I'm happy to introduce the machine learning platform that we have developed at MET. Again, my name is Abdelkader Mizgani. I'm working at the Norwegian Meteorological Institute. I've been mainly involved in the developing of the platform related to deployment of the machine learning algorithm at MET. So this fulfill the second objective of the WeaMyL project, which is about automated nowcasting warning systems by creating machine learning driven platform for early forecast of severe phenomena. So the outline of my presentation is the following. I'll start by saying a few words regarding the machine learning driven platform. And then I'll move to who is intended for. Briefly describe the different components, how the machine learning driven platform is linked to other WeaMyL components and MET Norway existing components. And I'll spend a little bit of time how to deploy and how it works, or how a user can use it. How it can be used to provide forecasts based on the different models that have been developed at Romania by the machine learning developing group. So the machine learning driven platform, as I mentioned, it has been developed by MET, and it's based on machine learning algorithm integrated within our post-processing infrastructure. We haven't really developed the algorithm itself. This was done by Babes University. But we have provided some expertise regarding the results, and actually we've had a lot of feedback and exchanges with the researchers in Romania and also the Meteorological Institute at Romania. So the main idea is to develop a nowcasting warning system that can be integrated within MET Norway platforms, existing platforms, in order to drive an early forecast of severe phenomena based on machine learning algorithms. So the main users of these developments are basically research meteorologists who will run the machine learning algorithm, and also the researchers can also search in the annotated atlas, as I mentioned previously, for some events or interesting events that can be used to evaluate different versions of the machine learning and different experiments and so on. But once this is done, I think the operational meteorologists will find it very useful to check the latest forecasts issued from some automatic jobs based on machine learning algorithms, review those warnings, and update or double check the generated warning with existing, for instance, forecasting systems at MET. So there are similarly to the annotated atlas, we have been using a series of tools in the front end, and then we've developed some specific jobs and connections using back end. So the front end uses data servers such as Threads, which is very known in handling netcdf files. And also to visualize the data, we've been developing an open source geoscientific web browser. I'll give an example of these tools later on, but the back end is mainly based on Python algorithms to run the machine learning models. And those are submitted to our post-processing infrastructure in terms of jobs, and it uses the CPUs or GPUs or whatever available to make things to run the scripts very quickly and in an efficient way, of course. This is the general picture of the WeaMyL project components. It's very complicated, but what I would like to highlight here is that you have different levels, you have different colors. So the dark blue represents the end users, as I mentioned. Here you have the researchers, for instance, that will use this platform to train some of the data and to identify some of the training data sets that will be used in the machine learning algorithm. The operational meteorologists that are responsible for issuing weather warnings, they will also evaluate the issued automatic warnings from the machine learning and then double check whether it is correct with other services and so on. Inside the blue box here, you have a combination of the front end and the back end engines of the machine learning platform. And in the gray colors, so these are mainly data sets or data providers. We have the threads here that has been implemented at MET. We have also threads at Meteorological Romania. We have also other systems linked to observational data sets, such as ground-based weather stations and other providers of data sets. So the machine learning model platform is this box here, which is responsible of processing the data and then producing a forecast. And then the forecast, in order to happen, it is linked to threads data server. So it scans, or it scans wherever any entry into the data, and then will issue a warning based on the latest, for instance, recorded data set. The data that we have used also is based on radar products, mainly the reflectivity factor. And then I'll say a few words about this afterwards. And we have, so this model platform here is connected to, it's not yet connected to the gap warning generator. This is something maybe beyond the project, but we've had a thought about it. But it is connected to the threads data server, and threads is connected to the GeoWeb web browser. So all the different components here are interconnected somehow and compatible together. And so as you can see, the system is very complex and it makes things very difficult to handle, especially the system administration box here that is not easy to deal with, because if one component or if some compatibilities breaks out, then the whole system should be revisited. All the affected parts should be updated as well, which makes it a bit difficult to handle at wherever there are maintenances in the different systems and processes. So if we move into more details, or take a look at the detailed components of the WeaMyL system. So those that are highlighted in the blue box here that I will be focusing on today The annotated atlas has already been described by Bart, and thank you very much for this. I'll be mainly focusing on the machine learning model platform, and then the GeoWeb as a visualizing tool of the output results. So the WeaMyL machine learning platform, it's in a simplified way. So we have the machine learning model script, which is a Python script that will collect data from threads. It can be the latest recorded radar reflectivity factor, for instance, but it can also be some historical events that happened in the past. And the script will digest this data with a bunch of pre-processing steps, and then use the trained data sets or the trained data sets configuration from that was provided by Romanian partners in order to produce prediction. So the prediction, there are two ways to do that. We have set up some automatic jobs that will run the script automatically every 5 to 10 minutes, as far as I remember. But we also have developed an on-demand job, which the meteorologist or the operational or the researcher will choose a specific date in order to run the algorithm, and then in order to make a forecast. To the right here, you have the description of the different command lines. So here we are in the Linux environment. All the things that have been developed are using libraries such as TensorFlow, which is a very known package used for machine learning developers, which we basically run a virtual environment using Conda, which is a package manager, and then we activate this working environment to get all the libraries, to get all the packages that are needed to run the Python scripts and so on. And once we enter this working environment, in instance here we have this production 10/2022, then we can run some Python scripts, as I mentioned earlier, by specifying an input, which can be the latest, the up-to-date forecast, or it can also be an earlier event. In this case, for instance, 28th of June 2022 at 10 a.m. So this is just an example given here. And once you run those jobs, then it will call for all the services that are behind in order to produce the results. But before going forward, I just would like to remind, maybe this has been said before, why we are choosing the reflectivity factor as a predictor or as a parameter to predict using the machine learning algorithm, because it reflects the power transmitted or returned to the radar after hitting water particles, so precipitation basically. So it's a good indicator of precipitation events or any event happening. So it gives an indication of the atmospheric situation, roughly. It doesn't cover all the different aspects related to precipitation, but it's a good indicator of strong versus or heavy versus low precipitation rates happening. It's a composite reflectivity factor, which means that we compile all returns from all the elevation scans, and we get the best estimate I will not go into details regarding to this, but I would like to mention that this Marshall-Palmer relationship that allows a straightforward transformation of the reflectivity into precipitation based on this relationship. So Z equals precipitation exponent sum coefficients, for instance, here. And the good thing about the radar reflectivity is that for low values, as for instance here you have this color scale, to the right you have the reflectivity factors, to the left you have the corresponding estimate of precipitation. And then for low values of reflectivity, usually it's drizzled precipitation, but when the reflectivity increases, then one would expect high or intense precipitation events. The learning functions, they have already been, I think, mentioned in the previous presentations, but I would only like to mention that we have been running 3 different versions. Briefly, as a reminder, version 0 will predict one time step based on the previous time step using a learning function. So this is an example of a typical reflectivity factor pattern with high intensity shown by the red color here, and the green shows low reflectivity values. And then we inject this into the machine learning model in order to make a forecast. So here we, as the input, it's the 16th of March 2021 at 6:35 a.m. and then would produce the upcoming 5 minutes forecast. So this is the first version we started with. And then it has been improved into using the 4 previous time steps. So this is version 1, which will also produce the same forecast, but based on the 4 previous time steps. And these are real reflectivity factor values. And as you can see, it doesn't really vary that much from 620 to 635. So that's why I mentioned if it would be maybe possible to aggregate in time in order to allow some variability and some temporal variability in the field. But then we will use the 4 previous time steps in order to make a forecast of the upcoming 5 minutes. The most recent version is version 2. It's much more complicated because it's based on 3 different models. So it's a cascade of models that will use the 4 previous time steps in a different way in order to generate 5 minutes ahead, 10 minutes, 20 minutes, and then 25, 5, 10, 15, and then 20 minutes ahead. So we use the 4 previous time steps as inputs in 3 different models in order to get the 4 upcoming time steps. As for instance here, we have the same field forecasted time at 6:40, 45, 50, and then 55. And as I mentioned earlier also, so all the machine learning working environment is based on Python programming language. It's based on Bash scripting language. So you have to define a specific job and then submit it to the processing infrastructure, for instance. It requires packages such as TensorFlow, X-Array, NumPy, CDF file to deal with file specifications and data specifications. And then I'm also using a climate data operator here to manipulate netcdf files. All the forecasts issued by the machine learning algorithm are stored in separate netcdf files. So you have one netcdf file for each forecasted time horizon. And then after, so the user should, or it can be done automatically, but we usually use the CDO as a compiler to merge those to merge like the different forecasted time steps into a single file if one would like to do that. One example of a PPI job, it looks like the following. So as I mentioned it previously, before. So basically, you need to activate the working. You need to activate the working environment, and then call this Python script. So this is the version here. You have this multiple ML models, which is the most recent versions, and then the user or the methodologist or the operational or the researcher or the operational methodologist can specify a specific time, or it can be set to the latest, as I mentioned, and then specify how many steps ahead to generate. It's been mentioned, I think, previously by the previous speakers that the far you go from the actual time, then the less good or the lesser or the results become not that good as one would expect, because of this cascade of errors that will emerge in the end of the generation process. So once you run this job, what you will see on the terminal, something like this one, so generated time, and which model and the version that it is used, and each generation time step will store the results into a separate netcdf file. So in this case here, you have generation or forecast from on the 16th of March 2022 from 6:40 to 8:35. So these are roughly, I think, 2 hours ahead. And then this is one example of the list of the files that the machine learning algorithm is producing for each or for different forecasted times. And then, as I mentioned, you can use the CDO merge time command to combine or to concatenate all the forecasts into a single file. Why we do this? It makes things easier when we visualize the results, and I'll show it later on. So I mentioned this complex diagram with the different components using threads for data as a data server, and then using GWeb or also Godiva as a web browser. So here, for instance, we've made Norway has made available all the reflectivity data factor on this threads data server, and we read the results from threads, and then we store the results on our local disk, but we expose them on threads again. So threads is used for reading and then outputting the results from the machine learning algorithm. And then we use a few tools such as Godiva that Bart presented before, but we have also done some extensions using this OpenGWeb, which is a more advanced tool. As an example of Godiva web browser, so I've made this this video here, which will based on data that the users can find on threads. You can select the predicted variable, in this case, the equivalent reflectivity factor for a specific time, and then you can make, like the users can make animations. What you need to specify the first time of the animation, and then the last frame of the animation, and then it will generate an animation like this one based on the produced results. And as you can see, that this is a typical reflectivity factor pattern. This is a specific event hitting Western Norway here, for instance. One of the limitations of Godiva is that you have to visualize one specific results on a time. You cannot, for instance, compare the results to the observations. And that's why what we spent time on developing this, or MET has contributed to the development of the GeoWeb platform, which allows importing different versions of the model and then together with the observation in order to have a better picture of the results. So this is mainly for visualization. It complements what has been done with the root mean square error calculations and so on in the training period, but put more emphasis on the results themselves. I think I'll try to show you how it looks like if we use this open GeoWeb platform, which is a web browser. So to the map to the left, it's based on the observation data set on the 16th of March, so the same event. The map in the middle is, I think, model version 1, I can't remember, but this is just for illustration purposes. And then the map to the right, it's a different model version. And what I would like to highlight here, I'm not saying that I do not want to say that the predictions using this version are bad or good, but the idea here is that with this open GeoWeb platform, it makes things, or it facilitates the work to the researchers, meteorologists, and the operational forecaster to visualize the results and compare them to the observations. And then one can give some like feedbacks and so on if something is going wrong in the results, as for instance this version here to the right, where you can see that there is a kind of discontinuity in the predicted reflectivity factor field. So this is something that I think have been fixed along with the project. But this is what MET Norway has been developing and working with. So we haven't really put emphasis on developing the models themselves, but we provided expertise in analyzing the results and ways how to visualize the results and how to run the algorithm into a broader way, including all the different components from reading data into producing the forecast and then visualizing the results. I go back to the presentation. Not this one. Yeah. Yeah. So this brings me to my last slide. highlighting some of the challenges. I've mentioned this earlier. With a complex system like the one developed within the WeaMyL project, I think we have learned a lot on how to implement machine learning algorithm, and then how to work efficiently in ingesting the data and then producing the results, and then dealing with all the workflow behind it. But there's still some challenges. I think the first or main challenge is regarding the forecasted results for 1 to 2 hours ahead. That the performance decreases quite rapidly if you choose a forecast horizon 2, 3 hours, 1 to 2 hours ahead. But there is also a challenge that I have personally been facing is the compatibility of the different components. As I mentioned several times, so there are many interconnected interconnected services and tools and so on. And if one system goes into maintenance, for instance, threads or our PPI infrastructure, then some of the links may break, and then it has to, or like the system administrator has to go through all the different details and try to figure out what was wrong, and try to figure out how to solve the different issues. We still need to work, I think, on some of the documentation to explain or to make and provide and maybe produce some user guides with all the details behind the machine learning algorithm platform, behind the annotated atlas as well, all different components and tools that have been provided within MET. But I'm quite happy, and I'm quite impressed how we went that far into this project, and how the communication and then the feedback from the different institutions have been made. I think we've learned a lot from both Romanian partners, and I think that's it from my side for today. Thank you very much for your attention.